Hello, and welcome back to Greg Does Physics. My name is Greg, and today we are going to be back doing some physics. Today we are going to be doing problem 4.6 from Griffiths' Intro to E&M, and 4.6 will ask us this. A perfect dipole P is situated a distance z above an infinite grounded plane, which Griffiths also shows in figure 7. The dipole makes an angle theta with the perpendicular to the plane. Find the torque on P, and if the dipole is free to rotate, in what orientation will it come to rest? So immediately to start this problem, we're asked to find the torque, and we should ask ourselves, what is the equation for the torque? Well, in the section immediately prior to this, 4.1.3, Griffiths derives and shows that the equation for the torque of an ideal dipole in an electric field is given by equation 4.4, which is this. The torque equals the cross product of the dipole moment and the electric field that it's in. Now, clearly, we already have the dipole moment, which is just given. What we need to calculate is the electric field of this configuration so that we can do this equation here. Now, if you're wondering how to find the electric field, your mind should go back to the previous chapter, chapter 3. Because in chapter 3, we have similar setups to this, where we have an infinite grounded plane, and then some charge distribution, and we're supposed to calculate the potential or the electric field or whatever of the configuration. And that's basically what we have to do here. So what we're going to do is we're going to use the methods that are developed in chapter 3 and apply them to this problem so that we can find the electric field of this setup. Now, what were those methods? Well, it's this thing called the method of images. The method of images naturally comes from the corollary to the first uniqueness theorem, which again is from chapter 3, which says that if you have the boundary conditions and the charge distribution for a given region, when you find the potential, as long as the potential fits that charge distribution and those boundary conditions, then regardless of how you found that potential is correct. And so if we create some analog situation where in the region where we're calculating the electric field that is above this grounded plane, and as long as we make sure that only in this region above the grounded plane we have our dipole exactly as it is, then whatever analog situation we use to compute the potential, that potential will be correct. And so then from the potential we should be able to solve for the electric field, and bing bang boom, we have our electric field to plug back into here. So then the question is, what should our image be? Well, to motivate what we should choose to be our image, let's go to the potential for a perfect dipole, and that is from the end of chapter 3. That is equation 3.99. The potential due to a perfect dipole is 1 over 4 pi epsilon naught dot product of the dipole moment with r hat over r squared. And so the condition, so again, we need to make sure that our boundary conditions are the same in both our original setup and the image analog situation that we're doing. And one boundary condition of that is that for any point where z equals 0, the potential has to be 0. Now recall that potential also follows the principle of superposition. So that is, if we were to place a second dipole down here, then we could compute their potential at a given point by just adding the individual potentials contributions from each dipole, which I labeled plus and minus, even though this isn't They aren't really like a plus and a minus charge. But we can imagine, we'll refer to this one as just the positive dipole for now, for lack of a better term. And so we want that to equal 0 for any point where z equals 0. And what that says is that based on this equation for the field due to a dipole, if we have two dipoles, our original one and then some other dipole down here, then we would want this to be such that this term for this dipole up here would be equal to negative of the analog term for the new dipole we're going to be placing in our analog situation. Now, so if we have some dipole that's a distance z below this xy plane, and again, you know, your instinct probably should be to just place a single dipole at the point opposite this one in the xy plane, because that's very much what we do in chapter 3 when the method of images is first introduced. In the very first example in which Griffiths introduces this idea, he has a positive charge q up here instead of a dipole, and then for the method of images he just puts a charged negative q down here. And so we want to think of what is our equivalent negative q in this scenario. Now, again, the potential needs to add up to 0 at any point in this xy plane. So if we can imagine, say we're taking it at this point here, and this is our r minus, this is our r plus, let's say, then we'll remember that we can think of the dot product as being composed of the product of the x hat, y hat, and z hat terms for each vector. And so if we want the whole thing to be negative, then the product of the x component of p plus and r plus should be opposite the product of the x component of p minus and r minus. Likewise with the y hat and z hat components. Clearly, the y hat and x hat components of script r are going to be the same. And so that means that for the x hat and y hat components, since the script r is going to be the same, also this should be script r. The reason I wrote it as just r is because that's what it's originally derived as at the end of the chapter, because the way that Griffiths finds the dipole contribution is by basically expanding the potential in terms of 1 over r terms, but if we're looking at the potential specifically for a perfect dipole, then we need to replace it with the separation vector. Anyway, I digress. So for the x hat and y hat components, our r's are going to have the same x and y components, which means the negative comes from the minus and plus from the dipole moment. And so therefore, the dipole moment has to be in the opposite direction in the x hat and y hat terms. But clearly, our script r's have opposite z hat components. The z hat component of this one is pointing directly upward. The z hat component of this one is pointing downward. And so the negatives, therefore, are coming for the z terms, is coming from the separation vector, not from the dipole moment, which tells us, therefore, that the dipole moment has to be in the same direction in z. So just looking at this dot product, we've concluded that the dipole moment has to be the two dipole moments, which were created in our analog situation, have to be in the same direction in z, but opposite in x and y. And so that would look something like this. So this therefore is our image solution, and clearly based on this, we've shown that it should equal v equals 0 anywhere where v equals 0. The other boundary term is that the potential should go to 0 at large distances, which it would, just because it's both the separation vector and the denominator for both of them. So the boundary conditions work here. And clearly, in this analog situation, since we're only looking at the potential in the region above the xy plane, our quote-unquote charge distribution, that is the fact that we only have this dipole here in this orientation, is the exact same as it is in the original problem. So therefore, we can be able to say that when we solve for the potential of this setup, that would give us the correct potential of this situation above the xy plane, which is all we need. And therefore, if the potential is the same, then the electric field should also be the same. And so then from there, what's our electric field? Well, the electric field due to a dipole is also given from last chapter, and that's given by equation 3.104. I solved for this in a prior video. And so equation 3.104 is that the electric field due to a dipole is 1 over 4 pi epsilon naught 1 over script r cubed, replacing script r with the normal r for the same reason as I stated before. Okay. Now for this equation, we need to use the electric field at the point where our dipole is. So we want to find the electric field at this point, 0, 0, z. That's the coordinate. And so at that point, the only electric field contribution would be coming from this dipole, because it's the point where this dipole is. So there will be no contribution from this, only from this dipole. So then let's look at this. Then it would become 1 over 4 pi epsilon naught. The separation vector clearly is 2z, so that's 2z cubed, or 8z cubed. And then our dipole moment dotted with the separation vector, which is from our quote-unquote source point to the field point, which in this case is just going to be positive z hat. Z hat minus dipole moment. And recall that in this case, the dipole moment in question here is this one underneath the xy plane in our analog solution. Now, in figure 7, Griffiths only shows us this setup in 2 dimensions. You have the z-plane, and then you're basically looking down the x-axis. So, for the sake of keeping it a little bit more generalized, I'm looking at this in 3 dimensions and saying that we don't know which direction phi it is, and this will make it easier to expand this into spherical coordinates, which is what we're going to do. Since we have this polar angle theta, which is going to determine the direction of our dipole moment. And so, I'm going to put this over here now, equals 1 over 4 pi epsilon naught 1 over 8z cubed. So it's 3 times the component of the dipole moment in the z hat direction. That's just what this dot product is here. And so the component of this dipole moment in the z hat direction clearly is going to be the magnitude of p times cosine of theta. And then z hat, and then minus oh gosh, darn it. Okay, technical difficulties, we're back. So we're subtracting the dipole moment P here now. I'm just going to put this as P, and then I would say that we could say that this is in the r hat direction. We could say that either of our dipoles here are in the quote-unquote r hat direction, which will give us a given phi. Some phi, assuming this is rotated some direction around the xy plane. But since we're saying that it's opposite this dipole moment in x and y, I'm going to put a negative on the x and y terms. So r hat in terms of the Cartesian components, you'll find this in the back of the book, and that would be this right here. So minus sine theta cosine phi x hat minus sine theta sine phi y hat, but it's in the same direction in the z. Cosine theta z hat. And so now we want to do, so now we have our electric field, we have our dipole moment. Let's just do this cross product. So equals 1 over 4 pi epsilon naught times, and so then we have a p term here, which we can take out, and we'll also have a p from our other dipole moment, so we can take out a p squared here. And then what we can do is we can do x hat, y hat. Well, let's just take this one step at a time. So first the original dipole moment, which is going to just be sine theta cosine phi sine theta sine phi, since it's opposite this one, and then cosine theta y hat z hat, and then our electric field. Oh, I didn't take the 8z cubed out either. That's line 8z cubed. P squared. So first off, so the negatives are obviously going to cancel out. Sine theta cosine phi. Again, cancel out. Sine theta sine phi. These do not cancel out, so it's going to be 3 cosine theta minus cosine theta for z hat, and so that's 2 cosine theta. And this should be, right here, our torque. Let me just double check that. Take the P out. P out. Okay, yeah. So now that let's actually do this. So let's see. P squared over 32 pi epsilon naught z cubed. X hat is going to be 2 sine theta cosine theta. Whoops. Theta. So x hat is going to be 2 cosine theta sine phi minus sine theta cosine theta sine phi. So that should just give us cosine theta sine phi. Sine theta cosine theta sine phi. Minus y hat, which is going to be sine theta 2 cosine theta cosine phi minus sine theta cosine phi, which again should just be sine theta cosine phi. Plus z hat. That'll be sine squared theta cosine phi sine phi minus sine squared theta cosine phi sine phi. So clearly that actually just zeroes out. But, again, go back to spherical coordinates, and we'll notice that the equation for phi hat is minus sine phi x hat plus cosine phi y hat. That's phi hat in terms of the Cartesian coordinates. But clearly, if we take out our sine theta, cosine theta, and we take out a negative as well, then what we're left with would be the equation for phi hat. So we can do that. So minus p squared sine theta cosine theta over 32 pi epsilon naught z cubed phi hat. Okay. But from our double angle formulas from trig, sine theta cosine theta could just be written as 1/2 sine of 2 theta. And so then we could do minus p squared sine 2 theta. I'm rewriting this because it'll be a little bit more illustrative for the last part of the problem, over 64 pi epsilon naught z cubed. Whew. So there's our equation for phi hat. So going back to the question, finally, we're asked if the dipole is free to rotate, in what orientation will it come to rest? It's going to come to rest when the torque on it is 0. And clearly, the torque on it is going to be 0 when theta either equals 0, pi over 2, or pi. But pi over 2, when it's like this, that would not be a stable point, because as soon as you push it in one direction, it's going to swing. If you push it, for example, in this direction, it's going to swing back up. If you push it in this direction, it's going to swing back down. And so the stable points for the dipole moment will be when it's at theta equals 0, so it's pointing directly upward and away from our conducting plane, or when it's theta equals pi, which is when it's pointing directly downward into the plane. And so if it's at this point, this unstable point here, you push it in this direction, it'll swing downwards. You push it a bit in this direction, it'll swing upwards, and that will be a stable point. It would swing back and forth around this stable point, theta equals 0 here. Likewise, it would swing back and forth like that around theta equals pi. And yeah, so that is our final answer. So thank you for watching.